Okay, we talked about polar coordinates and the working of polar coordinates. On Tuesday. And we'll go through, if you haven't done it, you should be doing it. You should have some polar graph paper there that I gave you. We'll take a look at a three-leaved rose, because the cardioid and the lemicons are pretty much the same. Did I have you do problem 21 or 22? I think I had to do 21, am I correct?
Yeah.
All right, so if we take a look at problem number 21, when sometimes you have, I know we did some things in regards to you have to plug in values of theta and solve for y or solve for r. When you have a three-leaf rose or four-leaf rose, what will happen is you'll just continue to repeat those values. If you go 30, 60, 90, 120, 150, 180, you'll just continue to go from the pole, from the middle, out to a point here, to the middle, out to a point here, to the middle, to the point here, to the middle, to the point here, to the middle, to the point here. And you'll just continue this pattern throughout. So what you will have to do is you'll have to do some intermediate values. And those intermediate values is you want to use values of 15, 30, 45, 60. You'll still be doing the exact same number of points, but you now will go every 15 rather than every 30. So if we look at r equals 3, r equals 4, cosine of 3 theta. I'm sorry, sine, yeah, cosine. Let's try it again. For sine of 3 theta. And once again, this is problem number 21. If you have not done it, I want you to run the values of 0, 15, 30, 45, 60. Run that through. Now, when you deal with your calculator, make sure you close your parenthesis out. So this is, for example, we have 4 sine 3, you have a beginning parenthesis times 15 degrees, and close that parenthesis out. Make sure you close the parenthesis out, because if not, you'll take the sine of 3, and then whatever the sine of 3 is, you'll multiply by 15, which is not correct. You need to take the sine of 3 times 15, which is 45. And then 4 times the sine of 3 times 30. Make sure you close that parenthesis out. And if you want to do mental math, that is fine. If you've not done it, please run this through. So running down these values, if we run down the values, Brianna Shanavy, what do we get if you run down your column of values here?
0, 2.8, 4, 2.8, 0, negative 2.8, negative 4, negative 2.8, 0, 2.8, 4, 2.8, and 0.
All right, those are values. So we have to go out, okay, we look at how big our values are, so we can't space this out like we did before, where I went, this is 1, this is 2, this is 3, because my graph wouldn't be big enough. Now your graph, I think, was a little bit bigger. You could probably space it out. So I'm going to have to go, this is 1 unit, this is 2 units, this is 3, this is 4, and this is 5. So if we go around, we have 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330. Now I know we didn't use these angle measures here. We didn't use these angle measures here, but we're going to need it because we're going to have to go out the opposite side. So if I start at 0, I'm at 0. And you get a very repeating type of pattern here. Once again, we're talking about a trig functions, and if you go back to the very basic ideas of trig functions, we called them periodic functions. Why? Because they continue to repeat itself over and over and over again. So at 15, we were at 2.8. So we're at 2.8. At 30, we are up at 4. At 45, we're back down to 2.8. And then we're back down to 0. Okay, and that takes our first 4 there. Then at 75, we're at negative 2.8. At 75, we're at negative 2.8, so we have to go out backwards since we have a negative value here. So rather than going out to 75, we're going out the opposite of 75, which is 255. It'll take us back on this line right here. We have to go out 2.8. So there's 1, 2, 2.8. At 90, we are at negative 4. So rather than going out 4 here, we have to go back 4. And then we're going to have a negative 2.8 again, and then we're back to 0. At 135, we're at 2.8. So at 135, which is this line here, we're at 2.8. 2.8. At 150, we're up at 4. At 165, we're at 2.8 again, and then we're back to 0. So what this allows us to have is it gives us some intermediate values here. So looking at my graph, I'm going to come out with my first leaf, and then we will continue this pattern here, and then back around again. And there would be our 3-leaved rows. Any other questions on graphing? The other graphs are a little bit easier because they're lemicons or cardioids, and then those you can use the 30, 60, 90, 120s. What I need to see on a test, okay, what I need to see on the test is you give me these R's and thetas here. You give me the r's and thetas. Now, let's take a look at our calculator. Because once again, your calculator is a very nice tool. And if you remember back from the very second lesson we had in this class, we talked about how your calculator can generate ordered pairs for you. Now, what I will want to see is I will want to see these ordered pairs. Okay, if we look at, I'm going to look at my memory here. If we take a look at my y equals, I hit my y equals button. Well, I got two graphs there right now, or two equations. I'm going to clear them out. So if you clear the equations out, let's type in the exact same function or y equals 4 times the sine of theta, or sine of 3 theta. So we have 4 sine of 3 theta, or I'm going to go 3x here. Now you need to make sure your calculator is in a degree mode. So I'm going to check my mode. I'm in a degree mode, so I'm good there. And I'm going to go to my table set, which is my second function in my window. I'm going to start it at 0, and I'm going to increment this out every 15 degrees. So if I now go to my second and my graph button, which is my table, what I get is I get the exact same values, but your calculator will generate them for you, which is nice. What I want to see, though, is I want to see these values here. I want to see the table. Give me a t-chart, or give me something that, or give me each of the ordered pairs on the graph. I need to see the ordered pairs. Now your calculator will graph a polar equation for you. Let's see here. If we would go to mode, down at the 4th line, there is a polar equation there. If we go over to polar, and then now go your y equals, now we're in r equals, and if we would type in your 4 sine of 3 theta, so we have 4 sine of 3 theta, close your parenthesis out. If we would go to a graph, I don't get it. Not sure why I don't get it. I'm sure I'm missing something. There we go. There's my 3 lead rows. So if I look, I get my 3 lead rows there with my graph. So your calculator will do polar coordinates for you. I'm not a huge change into polar coordinates and worry about a table then. You know, it gives you the same values of theta and r, that's fine. But you don't have to convert it into a polar units to be able to do that. Or you don't have to put it into a polar function to do that, because your values are going to be the same. I'm sorry, that for my table, the values will be the same. You'll get whether it's x and y or r and theta. Once again, calculator is a nice calculator. Take a look at page 280. Okay, doing conversions. Now, if we go down to the bottom, what you have to remember is our conversions. We have the sine of theta is equal to y over r, so y is equal to r sine of theta. We had the cosine of theta was equal to x over r, so x is equal to r cosine of theta. Then we had x squared plus y squared is equal to the r squared, or r would equal to square root of x squared plus y squared. Now, in the instructions on the review sheet, I asked you to describe the conic section. We didn't go over them, so don't worry about describing the conic section. But if we take a look at a problem down at the bottom, if we have y is equal to x squared, y is equal to x squared. Well, if we look at this, y is equal to r sine of theta. So we can substitute in r sine of theta, and this is equal to x squared, which is r cosine of theta, but we have to square that. Which we have multiplication between the r and the cosine of theta, so we're using our properties of exponents. We have r sine of theta is equal to r squared cosine of theta. Now, typically what we'll have, once again, as we talked about before, when you're dealing with polar coordinates, you want to have a final solution in an equation in r equals or r squared is equal to. Well, if we divide both sides by r, these r's would cancel. So we're left with sine of theta is equal to r cosine of theta. Then to solve for r, we could divide by cosine theta, cosine of theta. So this will give us r is equal to sine theta over cosine theta, which would be tangent of theta. If you remember your fond memories of all your trig identities. If we take a look at problem 3, 5, or 7, doesn't really matter. Let's take a look at 5. Problem 5, we want to change into Cartesian, so we have r equals 11 plus, or r equals 11 over 6 minus 5 cosine of theta. Now, if you follow our notes, what we did on Monday or Tuesday, Tuesday, we multiplied both sides by the denominator. So we took a look at this denominator here, and we multiplied both sides by it. So we had r times 6 minus 5, and cosine of theta. Cosine of theta is defined just as x over r. So we can substitute in our x over r. And this is equal to a value of 11. So I sort of did a substitution here of the x over r. Our next step was we multiplied through by the value of r. So we had 6r is equal to 5, or minus 5x. Is equal to this about is equal to 11. We can add our 5x to both sides. So on the left-hand side we have 5, or right-hand side we have 5x plus 11. On the left-hand side we have 6 times r. And this is the one where we had to substitute in the square root at this point. So we have 6 times r, which is equal to the square root of x plus y, x squared plus y squared. So we have 6 square root of x squared plus y squared. Our final step with this was the ugly, messy step, where we squared both sides. Over here we can distribute. Over here we have to FOIL. So one side you distribute, the second side we FOIL. So we're left with 636 x squared plus y squared, because we have to take 6 squared. And on the right hand side we have, FOILing this out, we have 25 x squared minus 55x minus 50, or plus 55x plus 55x plus 121. Once again, in a Cartesian form, this is an ugly equation. Distributing our 36 through, we have 36x squared plus 36y squared is equal to 25x squared plus 110x plus 121. Once again, a lot of uckiness. So getting it into the standard form, this gives me 11x squared plus 36y squared minus 110x is equal to 121. Which for your pre-calc fans or your algebra fans, this would be a conic section that would be an ellipse. Okay, these are the 3 types of problems that you'll see also on your quiz tomorrow. Okay, we will meet at 10 a.m. the regular time tomorrow morning. We'll just meet at the regular time. The review sheet is posted. The solutions to the review sheet are posted. Also provided for you. Questions you have? All right. That's all I have for you today. I just wanted to go over a few problems from my homework because it's not difficult. The material is not difficult, but it's just a little bit different. It's new to you. It's something you haven't seen before. So when you haven't seen it, and it's still, when you haven't seen it, it makes it a little bit more difficult to begin with. But once you see it a few times, it makes it a little bit easier to work with and deal with. All right, I have nothing else then for you. If you want to stick around, if you have a question or anything like that, that is fine. Other than that, I'm done for the day. That gives you an extra 40 minutes to work on your review sheet, do your review sheet and check your solutions. It gives you ample time to be able to do that. So that's, unless you have any other questions, feel free to stick around if you have questions. If not, adios, you out of here. Have a good day.
Thank you, Mr. Gregory.
Yep.
Yeah.
Yeah, we'll see ya.
Mhm.